Welcome back to online tutor. So the last 5 tutorials we have discussed about the complex numbers, and we have done so many theorems, right? And we discussed so many examples. I gave some homeworks as well, and so many students have been sent their homeworks answers as well. And thank you very much for it. I check it, right? And today, before starting the new theorems, I am going to discuss the previous day homeworks, because so many students told me, so how can we simplify it, like the inequalities or something like with the Lucas, right? So the last tutorial we haven't discussed the inequality cases, right? We just draw the circles, right? But actually the main format was z not equal r, right? So this is not an inequality, right? So the today tutorial I'm going to discuss about the inequalities as well with the homework examples, right? The first homework example, the first homework, it was z minus 3 less than or equal to, right? So here you can see we can interpret it like z equal x plus iy, z not equal 3 plus 0i, right? So this is my point, the origin complex number. So this is my variable straight line, right? It's varying with less than or equal to, right? It means this is my real axis, imaginary axis, right? So this is 3 now. Over here it's 3 and it's less than or equal 3, therefore 2, therefore it's moving like this way, right? Less than or equal means the line also taken, and the inside the circle we can take, right? So therefore the variable that this z complex number is on that, it can be on that the circumference of the circle, or else inside the circle, right? So wherever it can be located, right? So now you can see, now you can understand what will happen if it's only less than 2, right? So then you just need to draw the dotted line, right? Dotted line if it is less than or 2, right? But here it's less than, not less than, no, only not less than, it's less than and equal, therefore I'm drawing the complete circle. Okay, let's look at the next one. You can finish this, right? You can check your answers. Okay, the next one is z minus 1 greater than 1 less than or equal 3, right? So therefore the z minus z naught less than 1 then 3. Z naught mean again 1 plus I0, and these are my ranges, the radiuses, right? Therefore this is my real axis, imaginary axis, the instant complex number is 1 plus I0, it's over here, right? And the greater than is 1, it is passing through that way, right? It's greater than 1 and less than or equal 3. 3 mean here to here 1, here to here it's minus 2, right? It's like this way, minus 2. Therefore the z, my variable complex number is located somewhere here, right? Then I'm going to color the region, right? So therefore it can be located over here on the circumference, but not only that small circle circumference, it locates somewhere here, right? Actually you can write the coordinate of that point. It will be 1 plus 3 is 4, right? It's 4i, sorry, 4, the real part is 4, imaginary part is 0. Okay, so this is the diagram of my second Rome number. Let's look at the third example, right? So this is z plus 2 minus 3i equal z minus 2 minus 3i, right? Now I am going to use my, before that I'm just writing my variable is complex number x plus iy, then it's x plus iy plus 2 minus 3i, x plus iy minus 2 minus 3i, then it's x plus 2 plus iy minus 3, x minus 2 plus I y minus 3, right? So this is x plus 2 whole thing square, y minus 3 whole thing square. This is x minus 2 whole thing square plus y minus 3 whole thing square, right? So likewise we can square both sides, then square root will be disappeared. X plus 2 is square, y minus 3 is square, x minus 2 is square, y minus 3 is square, right? So likewise we can expand this. We can expand this. It will be x squared plus 4x plus 4, y squared minus 6y plus 9, x squared minus 4x plus 4, y squared minus 6y plus 9. So likewise, right, then x squared, y squared, 6y, all are cancelled off, 9x, right, plus 4, so you can see all are cancelling, therefore only 4x, 8x equals 0 is remaining, right? It means x equals 0. So what is that x equals 0? This is my real axis, imaginary axis, right? So always real x mean y, imaginary mean y, no? So x equals 0 means it's perpendicular. Right? This is the locus of that line. So the imaginary axis is the locus. Right? The imaginary axis is the locus. Why I simplified this, right? Why I simplified this? Because this is not our main format, right? So our main format is z minus z naught equal r. It can be less than or equal or greater than equal r. But anyway, it's not a something modulus equal to something another modulus, right? We have to prepare it to the we have to prepare it as the standard way, right? So what I did, I used the modulus definition to simplify it, and after that I got 8x equals 0, then it's x equals 0. Therefore you can see x equals 0 mean our x mean the real axis, no? X equals 0 mean it's perpendicular to the x equals 0. So surely it's imaginary axis. So the answer is imaginary axis. Okay children, this example, right, I'm going to construct it like z minus z naught 3 plus minus 3 plus I samana 2, right? So z is x plus iy, z naught is minus 3 plus I, right? R equal to. So how to construct it? This is my real axis, imaginary axis, called Argand diagram, right? So z naught is located at minus 3 plus I, it's over here, minus 3 plus I, and the radius is 2, no? So 2 mean the radius is 2, right? Obviously this is minus 3, no? Then it is minus 1. Then my axis is over here, right? Minus 3 plus 1. This is minus 1 and also this is minus 5. Okay, so this is my diagram of the locus of z plus 3 minus I equals 2, right? This is a circle, right? And also they ask the find the minimum value of z minus 1. So what is z minus 1? z minus 1 mean z minus z0, right? Z0 mean 1 plus 0 y. So z not over here. 1 plus 0 y. So it's over here. 1. Right? So I assume it's z not dash. Right? So we just need to find the minimum value. So you know, in a minimum value mean this is my line, right? So this is the furthest point, this is the least point, right? So least point is the minimum value, right? So you have to find that distance L. Okay, how to find this, right? You can see this is my right angle triangle, right? Here to here the length is 3. Sorry, here to here, here to there, it's 4. Right? Here to here, it's 1. And this whole thing, I assume L will be 4 square plus 1 square root 16 root 17. Right? So the minimum mean, Z minus 1 minimum mean root 17 minus this radius. The radius is 2 minus 2. Right? If you need maximum, then it will be root 17 plus 2 likewise, right? So this is the minimum and maximum value. So in this question we just need only the minimum value, that's all. Okay, so this is the diagram of the locus of this one, and I construct the z minus 1 and I put it and I draw the line to the origin, right? Line to the origin is always gives the minimum value and maximum value of the z minus 1. This is the minimum value, this is the maximum value, the furthest value, right? Okay, so hope you are the 5th row number. Now you can manage it, right? Try yourself. If you forget, if you are unable to do this one, and now the chance of you are to fill the 5th one, homework, 5th row number, right? Right, let's move to the next the other homeworks, the locus of the argument, right? Okay children, we'll see how to do this one, right? Argument z minus I. This is again z minus z naught, no? 5 by 2. Z naught is I plus 0. Z mean x plus I y. And therefore this is my so z naught located at imaginary, real here, and it's 90 degree. So the 90 mean this way, right? I told you to draw a non-shaded circle at the point 1, right? And also it is less than no equal no. Therefore this whole thing can be taken. I'm sorry about the second row number. So accidentally I put both less than, but it can't be the greater than 5 by 3 and less than 90, right? Please correct it, the question, right? So I accidentally put the less than for both. Okay children, let's move. We'll see how to do this, right? This is my argument, no? So R z minus z naught, z equal x plus I y, z naught equal 2 plus I 0. Right, so the angles are theta 1 and theta 2, 5 by 3, theta 2, 90. Therefore, this is my real axis, imaginary axis, right? So, this is my, the value is 2, right? 2 mean it's over here, right? 2 less than 90, less than or equal 90, greater than 60. This is my 5 by 3, right? It's over here. This is the complex number locate place, right? So I'm not going to explain third Rome number. We can move to the fourth one now after finishing this. So over here it's arg z plus 3 equal 5 by 3. We just need the modulus z minimum, right? So arg z minus 3 5 by 3, right? So z naught is minus 3 plus 0y, z being x plus iy. Therefore I am going to construct a real axis, imaginary axis, minus 3 0y. So minus 3 0y mean it's over here, right? So the angle is 5 by 3. This is my 5 by 3, 60 degree. Always we are rotating anti-clockwise direction, and the modulus z mean modulus z over here, because modulus z mean z minus 0, no? This is modulus z, right? Over here is 3 cos 60, 3 sin 60. So this is the minimum value, right? Minimum value. Minimum value, that z minimum will be 3 sin 60. 3 root 3 by 2. This is the minimum value of modulus z. Okay children, this is the last Rome number homework, right? Arg z plus 1, right? So what I'm going to do, I'm just constructing it z minus z naught equal 90, 5 by 4. Z naught will be then it's arg z minus 1 minus 5 by 4 minus 1 plus 0 z equal x plus iy, right? So the angle is 945 negative, right? Real z, imaginary z, real z, imaginary z. So it's over here, it's minus 1. Minus 1, the angle is 5 by 4. Sorry. So here the angle is negative. The negative mean it's moving to the other way around, the clockwise direction, right? I was wrong. So it's moving round, right? This is pi by 4 negative. Negative, right? Pi by 4 negative. Then z minus 1 mean z minus z naught will be 1 plus I0, no? So 1 over here. So this is the perpendicular line and the minimum value. Okay. So here to here, this whole length is 2, no? So 2. Therefore, this is 2 cos 45, 2 sin 45, right? Therefore, 2 sin 45. Therefore, z minus 1 minimum will be 2 sin 45, 2 over root 2, then it's root 2. This is the minimum value of z minus 1. And actually the important thing is, if the angle is negative, is, please rotate the clockwise direction, right? So rotate the clockwise direction, and also please clockwise direction, right? And if you need the minimum value, just draw the perpendicular line. And actually in this line we don't have the maximum values. The maximum mean it's going to infinity, no, we can't draw it, right? Always don't forget to draw the ring of the starting point, right? It's always non-shaded circle. Okay, so this is about my homework, right? So hope now you can manage this kind of Lucases, right? This kind of Lucases without any doubt, right? Okay, children. So this example now you can do as a homework, right? So the example was taken from the past paper book, right? It was 2003 A level, right? 2003 A level. So you can try it as a homework again. Right, now I'm moving to another A level paper question, right? This is 2013 A level question paper question. Let z equal x plus iy be a complex number where xy are real. Define the modulus z of z and the complex conjugate z bar of z. Okay, so the first one is definitions, right? So the z is x plus iy, no? So the modulus z will always x squared plus y squared. The conjugate of z bar, it's x minus iy. So these are the definitions in our lesson. And also after what they ask, prove that z modulus z equal z into z bar, right? So modulus z mean z into z bar, right? So how to prove this? I am starting from right hand side, right? So already define the z in z bar, it's x plus iy. The z bar mean x minus iy. When you simplified it, it will be minus I squared y squared. This is minus 1 x squared plus y squared. Therefore x squared y squared whole thing is square. This is modulus z square. This is my z bar. Therefore the proof was done. So after that, the next one is z minus z bar equal to I imaginary z. So you know z equal x plus iy, z bar equal x minus iy. If you added these, subtracted these two, z minus z bar will be x plus iy minus x minus iy, which is 2iy. 2iy mean imaginary z, because imaginary z mean y. Imaginary z mean y. Z minus z bar. Hence show that z minus 3i equal to z minus 3i modulus equal z squared 6 imaginary z plus 9. I am starting from left hand side. Z minus 3i square. So what is that? This is z minus 3i, z minus 3i conjugate, right? Because you know modulus z mean z into z bar, no? Therefore the modulus square of z minus 3i is equal to z minus 3i into z minus 3i conjugate. Therefore this whole conjugate will be z minus 3i z bar minus 3i bar, right? So what is that? Bar mean, the bar mean z minus 3i z bar plus 3i, no? Bar mean always the I imaginary part is changing their sign. So then now you can see this is z bar plus 3i z minus 3i z bar minus 9i squared. So 9i squared means plus 9. Then this is modulus z square. You can take 3i out, right? Z minus Z bar minus 9. So what is this? So we have already proved this. It is 2i imaginary z modulus z square 6i imaginary z plus 9. So this is my answer of the question, right? So it is z minus 3i whole thing square. Modulus square. So what I did, I start from left hand side and I state the definition, right, and I simplified it. So here if you put the modular conjugate of 3i, then it will be plus 3i. That's what happened. And the next one, deduce that z minus 3i greater than 1 plus 3i z if and only if z less than 1. Okay, so this is if and only if the both sides can be taken, but I am taking the left hand side. Z minus 3i, using z minus 3i less than 1 plus 3i z, I am going to show z less than 1. So now we have the property 1 plus the next one is you have to show 1 plus 3i z whole thing square is equal to 9 z square 6 imaginary z plus 1, right? So again I am starting from left hand side. 1 plus 3i z square, it's 1 plus 3i z 1 minus 3i z, right, bar 1 plus 3i z, it will be 1 plus 3i z bar, right? Then 1 1 1 3i z bar 3i z 9i squared z into z bar. This is 1, this is 3i, I'm sorry, this is plus, right? This is plus, then it become 9 minus, and also here minus 9 square, right? So because this is z and z bar, no, we have no chance to change the sign of that, right? So this is z, this is z bar, only z bar, z minus z bar. So actually we can take minus out, and here over here it's, this is modulus z, no, then plus 9 z, yeah, right? So this is again taken from the previous part. It's 3i 2i 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 imaginary z plus 9 z square. So this is 1 plus 6 imaginary z 9 modulus z square. The thing is how it be plus, right? Something wrong with my simplification. Yeah, something wrong, right? Here I was accidentally put minus on it. Here this is minus, this is plus, right? So once you take plus here and plus, then it will be I is minus, right? So I'm sorry about the simplification. So now it's okay. This is my 1 plus 3i z square, right? So this is my second equation. The first one also found, it was, the first one was z minus 3i whole thing is square modulus z square 6 imaginary z plus 9. This is my first term now, first equation, right? So after that, what they ask, deduce that z minus 3i, it's z minus 3i 1 plus 3i z, if and only if, right? If and only if mean the both sides, right? Only if this is less than 1. This is what they ask, right? Okay, I am starting from this side, right? I am starting from this side. We can substitute z minus 3 because this is, so we can put the square because we know this whole thing representing a positive value because the modulus is always positive. We can put the square because positive, right? So now 1 minus 6 imaginary z 9 z square, sorry, z square 6 imaginary z plus 9 greater than 1 minus 6 imaginary z plus 9 modulus square. So over here it's 2 getting cancelled and all modulus goes to one side. It's 8 the square, right? So 1 is going to that way, 8. Therefore modulus z square is 1, then modulus square is less than 1. So this is the answer of that deduced part in this question. Plot the points that represent the complex number z satisfying the condition z minus 3i less than 1 plus 3i z and argument z equal pi by 4 on an Argand diagram. Okay, so now we have this whole thing as a z less than 1. Okay children, so the next one is drawing these two, right? So we can prove this is equal to that, no? So if they want to draw this one, so it's possible to draw this z minus 1, right? Z less than 1. So what is z less than 1? So z minus 0 less than 1. So over here this is the diagram of z less than 1. So the radius is 1. Over here it's 1. Over here is minus 1. Okay. So then argument z, and we need argument z equal 5 by 4. So it's like this way. So this is my argument z by 5, z equal 5 by 4. So we know we need the both, right? So here over here it's always circle, no? Therefore the common region is this one, right? The common region. So this one region is the red color surface, right? So this is my z line, right? So the both are connected over here, right? So this is the common region for both this one and argument z 5 by 4. So this is 2013 A-level question paper, right? It's actually easy. The simplification and the proof are already there, but you have to prove it one by one, then it will be easy. Okay children, let's move to the next example. This is taken from 2012 LL paper. Prove that z modulus z square equal z into z bar and modulus z is greater than or equal real z. So how to prove that? Once z is x plus iy, z bar is x minus iy, and the modulus z is square root of x square plus y square, right? Then now what I'm going to do, I'm just starting z into z bar, x plus iy, x minus iy, so it's x square minus I square y square. This is x square plus y square, and this is square root whole thing is square, and this is modulus square. So this is the answer of the first one. And after that we just need to show z is greater than or equal real z. How to prove that? So actually modulus z means x square plus y square, no, right? So real z means, so actually real z is only x, and you can see x square plus y square is always greater than x, right? But if y getting 0, then x squared is equal to x, no, right? This because it's b square, but still it's root x. This is my real z, right? So comparing these two, right? Comparing these two, it's 1, 2, comparing 1 and 2, 1 and 2, modulus z is always greater than equal real z. So this is the answer of the first one. So basically it's depend on the modulus z. Right, so hence show that modulus z1 minus modulus z2 is always less than or equal z1 minus z2. How to prove that? So this is known as modulus inequality, right? So this is what we need, right? And I'm just starting from right hand side, right? z1 minus z2, but start with the square. So according to that, right, it can be written in z minus z2 into z1 minus z2 whole thing bar, right? Then it will be z1 z2 z1 bar minus z2 bar, right? So we can separately put the bars, and also z1 z1 bar minus z1 z2 bar, z2 z1 bar plus z2 whole thing, right? Plus z2 bar. This is z1 square, z1 z2 bar, z2 z1 bar plus z2 square. And I'm taking the all z. I'm taking z1 plus z2 together, and according to this, right, I'm taking minus out z1 z2 bar, z2 z1 bar. So what is this? This is the other important part. So this is z1 plus z2 minus, this is can be written in z2 bar plus z here z1 z2 bar whole thing again bar, z1 z2 bar again whole thing bar. So it will be again this one, right? So I think if it is z1 z2, it will be comfortable for you all, right? It will be comfortable if it is z1 and z2 in order, right? So after that, what I'm going to do, so this is basically z1 minus z2 square. Always children, if z1 z plus z, so z normally x plus I by no, z bar mean x minus I by no, z plus z bar, it's always 2x, right? Z plus z bar over 2, it's x. X mean real z. X mean real z. So the normally real z mean z1 plus z bar over 2, right? So over here, right? Over here, we don't have 2, right? I'm just putting by 2 and 2. Right? So what is this? So what is this? This is actually z1 minus z2 square, z1 square, z2 square minus 2. Here this whole thing is real z1 z2 bar, right? So it can be written in that way. So after that, what I'm going to do, so according to that, right? So according to that, modulus z is always greater than or equal real z. So I am just putting modulus z 2 bars, right? But here it's equal. But if you put this one, right? If you put this one over here, so this value is getting larger, right? This the value. So the normally z1 z2 bar is greater than real z1 z2 bar, right? So what I'm going to do, I'm just removing this part and I'm just put this one. So this one put me, it will be z minus z2 square, right? Then I'm just putting this, and the right hand side is this part getting more larger than, right? So something deduct mean this whole thing is smaller, will be smaller than the previous one, right? So then it's smaller means greater than or equal, this will be rising, right? Then it's z1 square z2 square, I'm just putting this minus 2 z1, so we can separate it z2 bar, right? So what is this? So what is this, right? So this is actually z1 minus z2 whole thing square, z1 minus z2 square, right? So these are all positive now. Then it is easy to remove the z1 z2 z1 modulus minus z2 modulus, right? This is the answer of that modulus inequality, right? So the modulus inequality in the modulus inequality of a complex number, right? This is actually some books in some books this theorem is known as triangle inequality, right? Then after we have to deduce something, right? Z1 plus Z2 less than or equal. So we have to deduce Z1 plus Z2 right. We have to deduce that. How to deduce that? Using the first previous result by 1. So actually Z1 can be written Z1 can be written with Z1 plus Z2 minus Z2, right? So what is this according to this one? Right. So comparing this Z1 plus Z2, this was written by 1. Okay, so this is the deduced part of that. So actually this is a special proof in our complex number lesson, right? අපි ඉනක් කොටසට යමු. ඉනක් කොටස අපිට කියලා දෙනවා if z minus I less than half, right? Show that three by 2. So we have to show this. So how to prove this? So here, over here, z minus I less than half. So using that result, right? Using that result. So our previous result one, z minus z2, it was always greater than or equal z1 minus z2, right? Using this result, so here z minus I, right? It is greater than minus I. So what is this? So what is this? Is it 1 minus I modulus mean 1. Therefore, modulus is it 1 plus half 3 by 2. Okay, so the other way around, I minus Z, it's always less than half, no? Right? So I minus Z also less than minus I modulus Z, right? And also it's less than half. Comparing these two, half less than the modulus I mean 1 is it. So the Z is 1 minus half. So modulus Z is 1 by 2. Right. So comparing these two results, so you can see our modulus Z is greater than half, less than 3 by 2. So this is the way of proving that one. So I will repeat it again. So here I took the data they have given to us and I use the modulus inequality proof, right? and I separate it, and here it's half less than this, half greater than this, and this one greater than this, and I connect these two and I construct 3 by 2. And also I take z minus I, and I minus z also same, no? So I put I minus z over here, and I again derive into 2, and I connect these two, and 3 by 1 minus half is less than z, right? So this is the modulus z greater than half one, this is the modulus z less than 3 by 2, then I connect both, and this is the final result of it, right? So I know this is very new for you all, doesn't matter. So again recall it, right? And try it again and again, and you will get the idea. So in my case, I'm also when I was studying this theory, so I remember this is very new for me, and I was confused what happened to there, and I tried so many times and I proved it so many times. Then after I prepared for that theory part, right? So actually this is a theory one, and in 2012 A-level paper was based on this theory in a complex number, right? Okay, the next part we have to shade it, right? We have to shade the region R consisting the set of the points of the Argand diagram representing the z minus I less than or equal half, and argument is z 2 5 by 3 less than 5 by 2. So what is this? So we already construct this as modulus z. We construct it as modulus z less than 3 by 2 and greater than half, right? How to construct this? Real z, imaginary z, right? So the modulus z means a circle, no? Circle means this is the circle, and argument is at this 5 by 2. Over here we have to draw a circle, and 2 5 by 3 mean 120. And what we have to do, right? So what we have to do, we have to shade the common region. We have to shade the common region. So basically the common region is this all, right? But not for that lines. So this is the common region. Okay. Capital R, the region. Okay children, this is about our 2012 LL paper, right? And also I put some homeworks to be done, right? So you can try this as a homework, and next tutorial I will describe this proof, and actually almost done, right? So the complex number is almost done. You can try any past paper questions, right? Any past paper questions, including new syllabus, all syllabus, all, right? So thank you very much for being with us, and have a nice day. I will catch you with the last tutorial in complex numbers.